Andrej Karpathy of OpenAI has done it again. He crafted a miniaturized Llama 2 over a single weekend, and it's already making waves with 10,000 stars on GitHub. This incredible repository allows you to train the Llama 2 large language model architecture from scratch using PyTorch. But that's not all. You can export the weights to a binary file and load them into a simple 500-line C file that performs inferences with the model. This repository truly offers a full-stack solution for Llama 2. Now you might be wondering, does one need a massive billion-parameter language model to achieve anything useful? Well, the answer seems not necessarily. Even very small LLMs can deliver surprisingly strong performance, especially when you narrow down the domain. Andrej recommends checking out the TinyStories paper for inspiration, which showcases how small transformers can achieve fascinating results. The pure C implementation ensures that this solution is not only easy to use but also highly portable, making it a perfect fit for various projects. If you're excited to get your hands on this model, check out the link to the repository in the description below. In this paper, the authors have leveraged sparsely activated mixture-of-experts, or MOE, to achieve remarkable performance levels in language models. Let's break down the key findings and understand how FLAN MOE outperforms traditional dense models. The authors first replaced the feed-forward component of every other transformer layer with an MOE layer, creating what they call FLAN MOE models. Each layer consists of independent feed-forward networks referred to as experts, and the gating function uses softmax activation to determine how well each expert processes the input. Unlike dense models, MOE models benefit greatly from instruction tuning, and they are particularly sensitive to the number of instruction tuning tasks. The study compared FLAN MOE to a standard dense encoder-decoder transformer across various model sizes. It was discovered that scaling up FLAN MOE led to remarkable performance improvements. For example, their most extensive model, FLAN ST32B, outperformed FLAN Palm 62B, while using less than 30% of flops per token. To evaluate the models, they trained them on 1,836 fine-tuning tasks and conducted zero-shot and few-shot evaluations on held-out tasks. The results were impressive, with FLAN MOE models consistently showing strong improvements across all scales. Particularly, the MMLU Direct benchmark witnessed an average performance improvement of 7.1%. The number of experts in the architecture plays a crucial role in FLAN MOE's performance. Initially, increasing the number of experts enhances the model's adaptability and efficiency in handling complex tasks. However, after a certain threshold, performance gains tend to saturate, especially in base-sized models. Routing strategy is another essential component in MOE models. Two strategies have been trending: token choice and expert choice. Activating more experts using the expert choice strategy has shown to improve performance across all benchmarks. To address overfitting issues, the authors incorporated auxiliary losses, promoting knowledge diversification among experts and improving the model's generalization capabilities. These auxiliary losses can also help with load balancing among experts and preventing expert collapse. To compare fine-tuning MOE directly with FLAN MOE, the researchers experimented with single-task fine-tuned MOE, single-task fine-tuned FLAN MOE, and dense counterparts. They found that FLAN MOE consistently outperformed fine-tuned MOE, especially when labeled data was scarce or when the model size increased. MOE models derive greater benefits from instruction tuning and are more sensitive to the number of instruction tuning tasks. Increasingly, MOE model performance scales better with respect to the number of tasks rather than the number of experts.
It just has to do with, well, okay, we can't really make models bigger than 220 billion parameters. We want it to be better. Well, how can we make it better? Well, we can train it longer. And okay, we've actually already maxed that out. We're getting diminishing returns there. Okay.
Mixture of experts.
Yeah, mixture of experts. We'll train 8 of them, right?
All right.
So, all right. So, you know. Okay, so GPT-4 is 220 billion in each head, and then it's an 8-way mixture model. So mixture models are what you do when you're out of ideas. So, it's a mixture model. They just trained the same model 8 times.
In a groundbreaking paper, researchers present CM3 Leon, a language model that combines retrieval-augmented, pre-training and multitask supervised fine-tuning stages. It operates on a decoder-only transformer architecture, removing bias terms, dropout, and learnable parameters for layer norms. The model utilizes a sequence length of 4096 and adopts a truncated normal distribution for weight initialization. But what sets CM3 Leon apart from its predecessors? CM3 Leon incorporates a retrieval approach to gather relevant and diverse multimodal documents from a memory bank. The retrieval process involves a dense retriever and retrieval strategy, utilizing a clip-based bi-encoder architecture. The key to sampling informative retrieved documents lies in considering factors such as relevance, modality, and diversity. In the text-to-image domain, CM3 Leon introduces a novel special token, which indicates transitions between modalities. The model also employs tokenization to encode images and text. For images, a custom tokenizer encodes a 256 by 256 image into 1024 tokens from an 8192 vocabulary, while text is trained with a vocabulary size of 56,320. CM3 Leon was trained using a metasequence squared method and is available in 3 sizes: 350 million, 760 million, and 7 billion models, corresponding to 1.4 trillion and 1.9 trillion and 2.4 trillion tokens. Interestingly, the model's losses steadily decreased during training, indicating that it hasn't reached saturation. CFG, or classifier-free guidance, enables unconditional sampling by replacing text with a mask token from CM3 objective. This means CM3 Leon can generate samples without the need for fine-tuning. The paper evaluates CM3 Leon using the Frechet inception distance metric and compares it to state-of-the-art text-to-image models. CM3 Leon 7 billion sets a new FID score of 4.88, surpassing other models like Party, while utilizing only a fraction of the training data and computational resources. Supervised fine-tuning, or SFT, is crucial for enhancing the performance of large language models. CM3 Leon benefits from fine-tuning across various mixed image and text tasks. These include text-guided image editing, image-to-image grounded generation, spatially grounded image generation, and how-to-write tasks, where users can request the model to create signs or logos based on text prompts. Figure 6 provides us with some fascinating qualitative examples of images produced by a fine-tuned CM3 Leon 7 billion model. From text-guided editing to structured guided image editing, CM3 Leon demonstrates its versatility and precision. In conclusion, CM3 Leon has revolutionized the world of multi-modal language models. It's showcasing its prowess in text and image generation tasks, with state-of-the-art performance and remarkable cost-effectiveness. Introducing HyperDreamBooth. This revolutionary hyper-network can efficiently generate personalized weights from a single image of a person, allowing for the generation of their face in various styles and contexts with remarkable subject details. Let's explore how this amazing technology works and how it outperforms other methods in the field. The foundation of HyperDreamBooth lies in composing personalized weights in a diffusion model. Combined with fast fine-tuning, this results in the ability to generate a person's face in diverse styles while preserving the model's knowledge of driven modifications. The beauty of this technique is its generic applicability, as it can be adapted to any text-to-image model. Before HyperDreamBooth, earlier methods using GANs or pivotal tuning faced challenges like poor subject fidelity or limited context diversity in generating images. But HyperDreamBooth takes a different approach, optimizing the entire text-to-image network weights to adapt to a given subject, ensuring higher subject fidelity in the output images. To achieve personalized generation, HyperDreamBooth is demonstrated on the Stable Diffusion version 1.5 model. This model consists of an image encoder, a decoder, and a UNet denoising network, which iteratively denoises a noisy latent code. DreamBooth provides a network fine-tuning strategy to adapt the text-to-image denoising network to generate images of a specific subject while retaining the generalization ability. To make the process more memory efficient and faster, LoRa comes into play. Instead of fine-tuning the entire network weights, LoRa proposes to fine-tune the network weight residuals with a small number of weights, leading to a remarkable improved performance even with a low rank of R equals 1. HyperDreamBooth also introduces LIDB, a personalized text-to-image model with a compact customized part of approximately 100 kilobytes. This achievement is made possible by training a DreamBooth model in a low-dimensional weight space generated by a random orthogonal incomplete basis. In the pursuit of enhancing prediction accuracy, HyperDreamBooth adopts a supervisory text prompt method, where the hypernetwork predicts LIDB weights of the diffusion model. The VIT image encoder and transformer decoder play essential roles in this process, providing better and more confident predictions through iterative learning. Through various comparisons and evaluations, HyperDreamBooth exhibits strong personalization results for diverse faces, surpassing the state-of-the-art methods in editability and semantic transformations. This method allows for a wide variety of style generations, proving its capabilities in producing high-quality and diverse face images.